So last time what did I go over last time? Yeah, we started sort of EEG and MEG, and I went over the grad div and curl on the 8 a.m. session, and so today we'll use div. We'll use grad and div to derive the current source density. So the problem now is we're sort of like, entering electricity and magnetism, and there's, all the letters of the alphabet have been used, B and D and H and E and J. So it's a big field, and we can't sort of cover the whole thing, but I just wanted to sort of go over this basic idea, which is directly related to this idea of divergence, where you have sort of parts of a vector field that are expanding out or going in, or doing neither, which would be like going around in a circle. And using that concept, we can get this idea of the current source density. And the current source density is just a number. It's not a vector. So it's a number that we can calculate. As we'll see, we can calculate it in 3D, or you can calculate it for scalp potentials as an example of what you can do. And so we'll just go over, like, what's the equation for it, and then how do you actually sort of calculate it in practice. And what's the point of this? Well, eventually, in a couple of days, we'll talk about source localization, sort of like where you're trying to sort of figure out where the sources are coming from by recording something from outside the head, or even inside the head sometimes. And that's a more indirect problem. If you could do 3D current source density, we'll see why that's difficult to do, because it's difficult to make the measurements to do it. But if you could do that, that would really tell you where all the currents were going in the head. And that's kind of like in some sense, that's like the sort of ground truth. If the data from current source density would essentially tell you where currents have, come from and where have they gone to, in a three-dimensional circuit. So to start off with, we want to mention that what we're doing here is a low frequency field approximation. So in other parts of this course, we've talked, without really going into the equations for it, about RF, or radio frequencies. And so radio frequencies are kind of a weird thing that people sort of conceptually invented before they actually had any method of generating them or recording them. But what radio frequencies are when the electric and magnetic field, disturbances in the electric and magnetic field propagate through space with nothing in there. So just absolutely zero in space, and you have some disturbance in electric and magnetic field that can propagate, millions of miles through space. And the reason this happens is that when you very rapidly change the electric or magnetic field, the electric and magnetic fields become coupled to each other so that they affect each other. So this requires that you have to sort of go fast, like just example, the example of MRI, we're doing 123 megahertz, so 123 million variations per second in the electric and the magnetic field. The electric and magnetic fields are always coupled with each other, but if you go through the Maxwell equations, you can see that the rate of change of them, which is in the coupling part of the equation, is divided by the speed of light. And so you have to go really fast before it affects. So they're always coupled. Even at very low frequencies, they're still coupled to each other, and messing around with the magnetic field can sort of change the electric field directly. But we're going to assume that that's not the case. And so so for the kinds of frequencies that you have with neurons interacting with each other in the brain, for all practical purposes, we can assume that those things are uncoupled. So electric field, that's E vector, uncoupled from mag, which is B or H. We'll just put B there. So they don't affect each other. But of course, we know that if you make a current, if you move some charges which are generating E fields, you get a magnetic field. But that magnetic field, so you say you have some current going through a wire, it generates a magnetic field around the wire. But that magnetic field, is not changing. So there'll be a fixed magnetic field as the charges move through the wire. So basically, what you can call this low frequency field approximation electrostatics or magnetostatics. So there's still sort of currents causing magnetic fields, or change in magnetic fields causing currents, but you can ignore this more complicated coupling that you get that causes radio waves. So basically, you calculate electric fields as if calc electric as if magnetic didn't exist. So and then we calculate magnetic field. So calculate electric field as if magnetic field didn't exist. Calculate magnetic field. From currents, from distribution of currents. So those are moving charges. And then we also ignore capacitive effects. That's not really part of the low field approximation, but so another thing that makes our life more difficult is that if you've got a capacitor is something that can sort of temporarily hold charges, and since currents are moving charges, some currents can sort of get bled off into a capacitor and sort of change how the electric currents are moving around. So for the purposes of the way we calculate currents in brain tissue at a sort of semi-macroscopic level, we would really have to consider capacitance if we were down at a single neuron level, but sort of at a sort of a mesoscale, we can basically ignore capacitive effects, and that will make our life also simpler. So that's where what we're starting from, and low frequency field approximation. And so now what we want to do is just talk about several definitions of the E field. So the E field, the electric field, the simplest way to think of it is if you have a charge, it's something that sort of happens around the charge. It falls off as you move away from the charge, but it's something that is done by the charge. Now, you can't really see it or see any effect of it unless you bring another charge in to sort of test it. And so that's one way of defining the E field is seeing what force occurs if you bring in a test charge. So it's a strange thing. It's especially strange when you get up to radio waves, because in that case there's nothing. You just have a complete vacuum, and you have this electric field with no charges around, no charges in sight, and it's somehow sort of affecting the magnetic field. The magnetic field is affecting the electric field, and then you get these propagating disturbances in these fields through space without any charges. But to start with, we think of an electric field as basically some weird thing, that's invisible thing that's done to space in a falling off fashion by having a charge in one place. But another way we can define it is by how we would measure it. And so one way we would measure it is, so here's the electric field, is to take the gradient of the potential. So the electric field is the negative of the gradient, the steepest uphill direction in the potential. And the potential or the voltage is a scalar. So that's this guy's the potential. You can sort of think of it like the pressure. Potential, it's a scalar. It's just a number, not a vector. And what does the gradient do? Remember, the gradient, it turns a scalar into a vector. So this thing, so the E is a vector. And remember, again, we're talking about this E is implicitly like a different E at each point in space. So we haven't sort of put the, it's really sort of like, the E field at a particular point in space, like that. But usually people just leave out that. So and that thing means like X, Y, Z, a vector that means X, Y, Z. So, but usually we just sort of just leave it out and just assume that that's what we mean. So, and the same for the potential at every point in space. So, so basically that's part of the definition of the, and this upside down delta is bold because it's a vector-like thing, because it turns this field of numbers into a field of vectors. And what's the definition? There's several definitions, but we could define this guy as the force. Remember, the force is also a vector. It has an amount in a particular direction. So this is, force vector acting on test charge. So if we put a test charge in there and see what the effect is. So that's the E vector, and then there's another term in here which we've already said we wouldn't include, but let's put it in here and then reject it. So it's the rate of change of the A vector. So that's yet another vector. So we said we would use up all the letters in the alphabet. So there's A and B. C is for the speed of light, and D is for displacement, electric field, and then E is for the irregular electric field. You use them all up. So what is the A? So the A is called the vector potential. Because that potential is the potential, so vector potential, and that guy. So how do we define that guy? So that guy is several ways to define it. So the way that Maxwell defined it was, it's the thing that when you take the curl of it gives you the magnetic field. So that's the curl So, and that definition was always so sort of troubling to me, like sort of backwards definitions. Like you've got something, and when you take the curl of it, then you get the magnetic field. That's what the vector potential is. But another way of defining it that's a lot more intuitive to me is to define it as in the following way, which is we've got some constants. So here, just ignore those constants. And then what you're doing is you're doing a distance-weighted sum of currents. So you're summing over the volume of the currents, and so the J, we use J to stand for a current density. So what is so as opposed to a current source density. So this is current density, and so current density is, how much current is there? That's the length of the vector, and what direction is it going? Because the charges could be going in any which way, and so that's the current density, and then, but what is it in the definition of the vector potential? It's weighted or divided by the distance of that current from the measuring point. So whatever point you're calculating A for, you essentially divide by the distance. So that means that the longer something is, farther away a current is, the less it's going to contribute to A. And so what is, so we can just say this is distance of current from a measuring point. So now you can sort of, that to me is kind of a sort of an understandable definition of the vector potential. So what it means is you go to a point in space, and then you look at where all the currents are around you, and then you divide each of them by how far away they are. That sort of makes sense in a way. And then you add up all those vectors. You sum up all those vectors, because all those vectors are going to be all these different currents in different directions, shrunken down by how far away they are, and then all added up into one vector. And so it's kind of an accounting for a particular point of where all the currents are and what their directions are and how big they are and how far away they are. So that thing affects the E field also, according to Maxwell equations, but now let's just cross that guy out. Okay, so we just ignore this guy. So ignore. Because we're doing this low, because we don't have this coupling business between the electric and the magnetic fields. Okay, so we ignore that guy. And so then our approximation of what the electric field is basically just the gradient. And so now let's just write out the gradient that we had before. And the gradient, remember, was just the steepest uphill direction in the potential. And so that's so basically this is approximately equal to there we go, to the negative of the change in the potential when you go in the x direction times the x unit vector plus the change in the potential voltage when you go in the y direction times the y unit vector plus the change in the potential when you go in the z direction times the z unit vector. So just the steepest uphill direction in the potential. So, okay, so that's the first there's only two equations. That's the first equation. So let's put that one in there, and we got rid of that guy. Make it simpler. Okay, so one last thing. One last thing, important thing about this is, if you look at this, the force, the force vector, acting on a test charge, what does that tell us? Well, that also tells us essentially, which way the current is going to flow. Because for a given E field, it's like pushing on the charges in a certain direction, and that's going to essentially, tell us, it tells us, which way current will flow. And, how fast will the current, or how much of the current will there, which way current will flow. So that's the other relevance of the E field. Okay, so now we need to do the divergence. So if we do the divergence, the divergence of this thing, then we get the current source density, which is, in words, is like a number that tells you how much a current is kind of erupting out of the void or disappearing into the void at a point in space. And so that thing is, and we'll make some examples of what it looks like. So here's the current source density. It's a scalar. It's just a number. So let's write it out. So current source density. And then we'll show next time how to actually sort of compute it for, like in 1D going through cortical layers, for instance. So the current source density is just equal to the divergence. So that was that other operation. It was the upside down bold delta times with a dot, like a dot product. So that guy is div, and it was kind of find radiatingness. So find radiating. That's what I call it. Radiatingness. So find how our vectors kind of like sort of spraying out or spraying in, or are they sort of more like going in a circle? And so it's finding the radiatingness of the negative of finding the steep hill the steepest uphill direction of the voltage of the potential. And so that thing, that's a scalar. Scalar field, meaning just numbers. And this guy is a vector, so how do we get rid of the vector? So if you go back to how you calculate the divergence is basically just how rapidly is the x component of the vector change when you go in the x direction, plus how rapidly does the y component of the vector change when you go in the y direction, and then how fast does the z component change when you go in the z direction. So if you look back at this equation, this thing is exactly, so that thing is a number. So this guy's a number times the vector. And that's the number we want for calculating the divergence, which is how fast did the field change when you went in the x direction. And so, but you're taking that's already that number, that single number is already a derivative. And so you've got to take the derivative of a derivative when we do this this divergence operation, because the divergence operation was like, see how fast the x component of the vector changes when you go in the x direction, but the x component of the vector is itself a derivative of the, it's actually a derivative itself of the potential. So it's a second derivative of the potential. So what that boils down to is it gets rid of the vector part. So this guy is the unit vector, but since for calculating the divergence, we only care about the number part, we can sort of toss the vector, and so you just end up with our final answer, which is just the second derivative of the potential. So it's the second derivative of the potential in the XYZ directions. With no vector now. So this thing is just a number. And this thing, so this particular thing, which is so what is that? That's the second spatial derivative of potential. So that thing is often written in a different way. It's often written as a non-bold upside down delta squared. So it's not bold anymore because this thing is a scalar field. So we kind of started with a scalar field, we went to a vector field, and then we went back to a scalar field. So this thing is called the Laplacian. And what that means is it always implies a spatial derivative, because we could have a temporal derivative too, because things are changing over time. Like here, things are changing over time. But this thing implies a spatial derivative. And so the bottom line is very simple. It just says all you have to do is just take the second derivative of the potential field, and that tells us the current source density. And you don't have to worry about vectors, really. So that's basically our current source density. So now what we want to do is just get some feel for, like, what it looks like, or how do you calculate it. So what is fundamentally, what is the second derivative? The second derivative is basically the curvature. So it's the curvature. So what is, so let's just sort of do this second derivative, a simple second derivative in one dimension, just to see what the curvature is, and then see how you would estimate the curvature. And then we have to be able to. So one of the things when you're first doing this, at least if you're like me, you don't have much math background, you get confused with second derivatives and different dimensions. So this is, don't get the dimensions and the derivatives and the level of the derivative mixed up. So here, this is a three-dimensional second derivative, but we could do a one-dimensional second derivative or a two-dimensional second derivative. So let's just do a one-dimensional second derivative. So imagine, you've got just a curve like this. So that's clearly a curve that has some curvature in it. And so now let's go someplace on that curve. Let's go someplace on that curve. And so what is the derivative? The derivative is just the slope. The derivative is the slope. But what's the second derivative? Well, it's just the derivative of the slope. So how fast is the slope changing? And how do you, what's a simple way of estimating that? A simple way of estimating that would be to go out a little distance on the curve and and then take the average. So here's the average of two neighbors. So let's just write this out. So first derivative is just the slope. So second derivative is estimate. So what's the second derivative? It's just the you write an equation for the slope as a function of x. Say it's x down here, and then you take the derivative of that equation, and you get the second derivative. But how would you actually sort of estimate it in practice with a finite difference? So the second derivative estimate is basically compare center point to average of neighbors, or subtract of neighbors. That compare means subtract. So compare, subtract. So let's just look at it in this case. So if we go out a little distance on either side and get whatever the value of the function is there, and average that, you get something in the middle. There's the linear average. And then if you look at the actual point, you can see it's down, and so that's going to be that will tell you what the sign of the second derivative is. And alternatively, you could do the same thing. Imagine you have a curve, that's going like that. As you go up in x, how do you calculate the second derivative? You would so the first derivative, will be a slope, but the second derivative will be, let's go out a little distance and then average the neighbors and look at where you are relative to the neighbors, and you can see you're kind of sticking out in that case. And so that's in 1D. This is 1D. All we have to do is just do it in 3D. So to estimate this second derivative here. So it's the curvature. So curvature is sort of easy to sort of conceive of with a simple graph like this, but it's a little harder in 3D, but you can sort of get the same idea. So like you go to a point in 3D, and what does it mean for the curvature? Well, you got to go out in all the XYZ directions and sort of average those guys, and then figure out what their average is compared to what your value at the center point is. So it's kind of a local measurement of the curvature of the potential field. So what is it? So how would you actually kind of measure it? Actually in a brane, and this has actually been done. So you would basically go. So here's a brane. You can see what the problem is immediately. So here's a little chunk of brane, and it's got here's a pyramidal neuron in the brain like that. That's one pyramidal neuron. There's like another pyramidal neuron in the brain over here. And so now all we got to do is just, at each point in the brain, measure the potential so that we can calculate the local curvature. So how would you do that? Well, you would just go here and here and here and here and here, and then measure the potential there, and then go here, and then go back deeper in the brain. You can see what the problem is. You'd need to make thousands of measurements in that little chunk of brain, and that would be hard to do without sort of damaging the brain. It's actually more possible than you think. So if you take a microelectrode doesn't do very much damage at all. If you put a microelectrode in the brain, it kind of more or less, it just sort of pushes stuff off to the side, because the brain is like, you can think of the brain as like felt. It's like this completely interconnected series of little wires all sort of going every which way. If you put a very sharp electrode in there, what it'll do is most of the wires will just bounce off the electrode, and so the electrode will just go down into that felt, and just like a pin going into felt, and just move stuff aside. So it actually doesn't do as much damage as you might think if it's a fine electrode. So what you can do is you can put it in and then slowly pull it out, and then make measurements of current flow by doing some kind of stimulus over and over again, 10,000 times or so. But you can see that this would, if you did this and then calculated the current source density, it would tell you essentially where all the currents went and came from, and and it would be like the bottom line of like what actually happened in the brain. So that's the interest in the current source density, because it really tells you what happened, where the currents came from, and where they went to, and you would really understand how the circuit was working, because you would see some current went into this pyramidal cell and came out of this pyramidal cell, and that caused some other basket cell to become activated, and so on. You can see the problem. The problem though is you need a lot of measurements in order to do this. So that's going to be the main issue. And so what people have typically done is they've done either 1D current source density, just measure current source density along one axis, or measure 2D current source density across the surface or even across the scalp. And then occasionally they've done experiments like this where you actually measure the bottom line, which is 3D current source density. So let me just do one more little diagram of the divergence as opposed. So here we're talking about calculating the second derivative, which is not a vector. It's just like go out in the XYZ directions and take the average of your neighbors, and then subtract that from your current value of the potential at the point. But let's just sort of look at what the divergence calculation looks like. So the divergence calculation is kind of calculating how sort of radiating are the vector fields. And if you have a vector field like this that's kind of straight, then when you calculate the divergence of that guy, so say these are the E field, this is the electric field at each point here. So when you calculate the E field, hold on, sorry. Let's see, I'm not going to answer that. Okay. So when you calculate the divergence, are these guys radiating at all? And then how do you calculate that? Remember from the lectures, you go out in the x direction and look at how the x component of the vector changed, didn't change. You go in the y direction and see how the y component of the vector changed, it didn't change, it was 0. It was whatever it was here. So you just compare sort of x component to x component, and why don't we make some that are tilted so you can see the x and the y components. So when you calculate that gradient estimate, the divergence estimate. So say we have vectors like this. So there's no divergence here because we look at here's the x and the y components of that vector, and if we compare x didn't change to x and y didn't change to y when you go in the y direction. But what is another situation that has vectors pointing in different directions that still has a 0 divergence? So this guy's the divergence. An example would be something like a circulating field. So I got to put some circles in here so I get my vectors correct. So if you had some kind of circulating field, so that would be like a vector that's like that, and a vector that's a little bigger in that direction, and a vector that's a little bigger out here. So those are in different directions, but if we break those guys up, what you'll see is that if we compare the x component here as we move in the x direction, it's not different. So it's, the x component is 0 in both cases. But if we compare the y component here, the y component's not different either. So it's same here, and since our derivative is a difference between those two. So if the vectors are sort of going in a circle, then you also have a divergence of 0. And then one of the other possibilities for a positive or a negative divergence, that would be cases where the vectors are sort of either radiating or kind of going into a point. And what would that look like? That would look like something like, say the vectors are slightly radiating like that. That would have a positive divergence, and that would be because if we look at, as we go in the x direction, you can see the x component of the vector got a little bigger, and then as we go in the y direction, the y component of the vector got a little bigger. So here's the y component of the vector got a little bigger. So that guy would have, this guy would have a, if you had an E field like that, this guy, would equal a positive divergence. That's sort of radiating this. And then similarly, if you have something, that looks like this. So notice they can all sort of point roughly in the same direction. Like, here's a 0 divergence. They're all sort of more or less at 45 degrees. Here's a positive divergence. And then here's a negative divergence. So they're all pointing off to the right, but again, you can see that in this case what happens is when you went in the x direction, it got smaller. So that component got smaller, and then this component also got smaller. The y, when you went in the y direction, the y component got smaller. So that's the divergence, the current source density. So the current source density is basically how is the electric field geometrically arranged, around each point. Is it arranged in sort of kind of like an expanding thing or a shrinking thing or just circulating? If it's just circulating in a circle, then there's nothing sort of coming in or going out of that point, and that's a 0 current source density. So 0 current source density doesn't mean that there's no current there. There could be current. It's just like if it's just going around in a circle, then it won't be sort of erupting out or disappearing, and that's what we're interested in. Okay, so that's the current source density. So let's just stop for a second and talk about the current source, see if there's any questions about the current source density. So what it is, it's a way of sort of measuring the ground truth of where the current sort of came from and where it went to. And the way we measure it, you actually don't even have to mess with this divergence stuff down here, because once we do the divergence calculation on this this gradient, we end up just with the simple spatial second derivative, which doesn't have any vectors in it. And the second spatial derivative is just the curvature of the potential field. So the way we measure it is we just make a bunch of measurements of voltage in 1D, 2D, or 3D, and then we just compare each measurement to the average of its neighbors. So the measurement of it is actually very simple. You don't have to bother doing vectors. But you do need a lot of need a lot of actual measurement numbers. Okay, so questions about current source density? So we should just put up a couple. If you ever, open up electricity and magnetism textbook, you'll see several other letters in there, and so let's just put those in. Just write those up. So, and then just say what the forward and the inverse solution actually are. So let's first just start off with some of the other letters. So another very simple relationship with this current density is called Ohm's law, and that just says this is what I was saying, like right up here. So in a very simple setup, there's more complicated ones, but in a very simple setup, so that's Ohm's law. And what is it? It just says the current density is just proportional to the electric field. So this thing is called the conductivity, which is the reverse of resistance. So more conductivity means less resistance. And so this guy is the electric field, and this guy's the current density. And so that's what the E field is good for. It just tells you how much current and what direction is the current going to go. But there's one more thing, which is what is the current going through? And so when you actually start to consider things other than a vacuum, different substances are going to let more or less current through for the same E field. So if you put a given E field and put something in that doesn't conduct current very well, not much current is going to go through. So that's basically Ohm's law for a very simple kind of substance. And then there's two other ones that we should mention, and these have to do with the magnetic and the electric field. And so you might often see the magnetic field written as H. And so what H is kind of a similar kind of thing. It's equal to 1 over some constant, and this constant is called the permeability. And it reflects how the magnetic fields can go into a particular substance. And so for a given sort of magnetic field B, or magnetic induction B, depending on how permeable the substance is, you'll end up with more or less sort of macroscopic magnetic field. So that's what the H is. That's the magnetic field you would actually measure. So the B would be the magnetic field that you'd expect to be induced in a vacuum if you ran some current in a direction. So that's the H. And then you might also see D. And so D is another one that has to do with how easy it is to polarize something. And so it's kind of another version of the E. So this thing is called the permittivity. How permissive is it? is something. And what this means is, polarizability. Ability. Okay, so now we got all the letters covered, all the letters that you might see if you look at Maxwell's equations. So again, this varies with different kinds of substances as opposed to a vacuum. So if you've got a whole bunch of atoms there and they've got charges and everything like that, and you apply an E field by, say, putting some charges outside of that thing, how polarized the actual substance ends up can vary. And again, that's there are more complicated ones that aren't linear like this, but this is like the most sort of basic definition of all the letters that you're going to see. Okay, so this current source density was a way to sort of calculate, a way to measure where the currents are coming from and going to. And it's kind of the ground truth, but it's very difficult to measure because you need so many measurements of the voltage, of the potential at each point. So what are we going to talk about next is the forward and the inverse solutions. And what those are just more indirect ways to try to estimate where the current, is actually going. And so when you talk about the forward solution, so here's the forward solution. What are you talking about? Talking about, so the forward solution is, we've got some brain in there. And what's going on in the brain? There's J's going on in the brain. There's currents going in every which way. So here's some J's going on down there. And so those J's, what are they going to do that we can measure? So here's some J currents all over the place. They're going to generate something that we can measure as a voltage on the scalp, and then something that we can measure as a magnetic field on the scalp. So the magnetic field is a vector. The current is a vector. The potential is so this is this is voltage, potential, and this guy is magnetic field. And the forward solution is, for a given amount of current someplace, how much magnetic field and how much voltage do we get? So that's something that we have to, before we can try to figure out where currents are coming from in the head, we first have to do that. We first have to make a model that says, for a given amount of current pointing in a certain direction, somewhere in the brain, what voltage would we expect to measure at this point on the scalp, and what magnetic field would we expect to measure at that point on the scalp, and what direction would it be pointing? So that's the forward solution, and we'll talk about how you could try to estimate that. But then what we really want to know is the inverse problem. So the inverse problem is just exactly the inverse of that. So the inverse problem is, we recorded some voltages at all these places on the scalp, or we recorded some magnetic fields. And so the inverse problem is, where were the currents? So given this set of voltages, where would we expect the currents to be? And this is a much harder problem, and it's just kind of in fact, there are multiple possible situations of where the currents could have been that could give rise to the exact same data. And so it's a much more ambiguous situation than the case of current source density, where we just put the electrodes in, we measured all those voltages, compared them to their neighbors, and we just figured out where all the currents were going. It's the bottom line. So this is what we're going to talk about next time, which is a more indirect and more sort of error prone and more underdetermined, in the sense that there's multiple situations of currents that could generate the exact same measurements here. So okay, so that's sort of derivation of current source density. What we'll do next time is talk about actual measurements of current source density in brains that have led to the whole concept of this radial current flow. So where did the concept of radial current flow in the cortex come from? It came from actually measuring current source density in the cortex, and that's why we end up modeling these currents as little current dipoles, and we'll try to explain what it means to be a current dipole. And so explain why we think there are current dipoles. That's from doing current source density measurements, bottom, baseline measurements, and then just try to say what a current dipole is, and then finally, how do we possibly estimate what a current dipole is given some data outside the head. Okay, so any current source density questions?
You defined the A vector earlier, like your top right.
Yeah.
What's the differential in the integral? Is it like the dr vector or something like that?
Oh yeah, it would be like sort of, you just say like, d volume. So it's a volume element. Yeah, sorry about that. Left that off. Yeah, so what you're doing, so basically for each little volume element, find whatever the current is, what the current direction and amplitude is in that little voxel, divide it by how far away you are from your current your current A point, and then sum the whole mess up. So it's kind of like you can sort of think of it as, it's just a way of sort of accounting for, what all the currents in the whole universe are affecting just you. And that one, like in quantum mechanics, that's the main one you have that you use in quantum mechanics, as opposed to E and B. Okay, so any other questions about the current source density? So current source density, a lot of times in ERP, you don't hear too much about current source density, but in some respects, that's the really good one, because the potential, I mean, an example is like, say here's your head, okay, and say there's, say here's 0, and then say you've got like a positive evoked potential, something like that. So that's your evoked potential. If that evoked potential is kind of negatively curved, even though it's positive, that means a different thing than when it's sort of positively curved. And so just the sign of the evoked potential is not very informative as to whether current is coming or going. It's really more just like the actual sort of shape, the curvature of the potential field. So if you do an evoked potential and you find a big positive evoked potential over here, you have to actually check the curvature of it, because it actually might indicate current's going the opposite direction. It's not coming out of there, it's maybe going in there. So we'll talk about that, talk about actual data from real brains and why we think that, there are current dipoles and why are they oriented perpendicular to the cortex from actual measurements. Okay.